live, folks. We're live. Something was up with the audio. I don't think this thing was fully charged. So the last lecture, kind of when I spoke, it would drop the audio. The video was there, but hopefully it'll stay charged. All right. All right. Questions? We're okay? No, Anton? You had a question?
Just with your switching code with the SD and SCD.
Okay. I think what was that running at on the 2560? Yeah. Yeah, because I needed a lot of memory. 2560. All right, I updated the slides again for the final time. All right, I took a lot of stuff out. I took the I/O stuff out. I took a lot of math stuff out. Just these set of slides are for chapter 1 and 2. I have another set of slides I'll post up there. Just going to be chapter. I'm going to go chapter by chapter. Okay, just to keep things so you know exactly where we are now. Over to quiz. Sure. Oh. Just let it warm up for a second. Everybody get the email? Homeworks? All right. We're finishing chapter 2 today. We're moving on. Well, I have my colonoscopy at 10 tomorrow, so I'll be home by about noon. I'll be all full gassy, and then I'll, just kidding. They should be up tomorrow afternoon. I'm just kidding. I do have a colonoscopy tomorrow.
Is that what we should have done for Friday's class?
What, chapter 3? You should start reading it. Just reading it, yeah, but I won't quiz you on anything on chapter 3 because I haven't covered anything. All right, quiz number 2. Okay, here we go. What happened to my... It was up a minute ago, right?
Yeah, it was.
Come on. Come along, projector. You were up a minute ago. All right. Solution to quiz. All right. Let's start off. Let's just take the first one, okay? And let me expand this. There's a way to. All right. You're all right. The question was. Just load the hex values of 30 and 97 in the memory locations 105 and 106. Okay, and all we had to do here. Can everybody see this? Is this okay? All right. A couple of things about this instruction set. All right. All right, LDI, some folks tried to do an LDI. Let me get this powered up. They tried to do an LDI 10530. What is LDI used for? Loading into a register only. Only. In order for me to get something into SRAM, I have to load something into either R16 through R31, then transfer it using STS to get it over to where I need to get it into SRAM. You have to load it into a register first. All right? I don't know why, but folks were putting in, instead of R20 or a register here, they were putting in that physical address right there. It doesn't, it's just the command does not work that way. LDI is purely for registers, okay? It's purely for registers, all right? So here I just bop it into R20, take it from R20 to 105, put the 97 into R20, put it into 106. The STS command, all right, let me just go to this PowerPoint for a minute because I want to summarize these. All right, let's look at the LDI command again, all right? Boy, I don't like this. I don't think that's recording the screen. All right, we'll see. All right. If you notice, LDI is to load a register with a value. It's loading in immediate. It's an immediate load. K is, say, a hex number. How big can that hex number be? How many bits? 8 bits, because every single register is how many bits? 8 bits, all right? Every register is 8 bits, so, and then if you notice here that it can go from 16 to 31, you cannot load immediately into register R0 through R15. That's just the way it's set up. The number that you can load it in can go up to 0 to 255 decimal, which is FF hex, 8 bits. 8 bits, all right? That's what we got, all right? So that's the LDI instruction. So you got to make sure, if you don't know this instruction set, you're done. You're cooked, okay? It's just the way it's going to be, all right? And the only way you're going to get to know this instruction set is to grab the code on those slides and run it. That's why I put it up there. You don't run the code, you're not going to understand the code, you're going to bomb. I mean, it's just not going to happen, okay? So let's, I don't know what else. If you're going to give me suggestions on another way we can figure out how to learn how to code without understanding what an instruction is, I don't know how it's going to happen. Okay? All right. When you do an add instruction is, again, it's a 16-bit, 2-byte instruction. And you can only add from one register to another register. That's what the RD and RR stand for. You can only add the 2 registers together. I can't go from a memory location to another memory location here. It's only for one register to another register. All right? And it's a 16-bit instruction. This is 16 bits. And again, I can use any register I want here. The destination, that's what the D stands for. The destination register can be from 0 to 31. The other register can be from 0 to 31. That's it. The add instruction, and you have to look at this. This is all summarized in Appendix A, gang. Every instruction is summarized in Appendix A. That's where I get this stuff from. I pull it right out of Appendix A. All right. The STS instruction, it is a 4-byte instruction. Why is it 4 bytes? Or we shall say 32 bits, right? 8 times 4 is 32. Why is it 32? Why is it 32? The other ones, if we go back, these are 16 bits, 16-bit, 16-bit. Why is the store in SRAM a 32-bit instruction? Where am I storing it at? I'm storing, no, not 32 registers. We're storing it in SRAM. All right? SRAM is outside of the registers, okay? How many, okay. Again, let's go back and think about this. These are subtle little things, but they're fundamental to understanding what this processor's doing, all right? SRAM. All right, let's just take it, to, let's say, what do you want to do? 169p. I think it's 04FF. I'd have to look it up. 04, whatever. If I was on the 2560, I would have this. The size of SRAM is different for each one, right? However, how many bits do I need to address a memory location? I need 16 bits. That is why STS is a 32-bit instruction. If you notice all these little K's down here, it is to store a register in memory location given by K. What does K have to be? How many bits? 16 bits. So therefore, we have up here, we have the opcode and the other stuff is going to take up the first 16 bits in here. And again, the K's here go from 0 to 65,535, which is FFFF. Yeah.
So that has to be from a register. You can't store from a location to it.
What's that right there?
Register.
Register. So you got to understand the subtleties of every command. Here goes to a 16-bit address, STS. So when you look at the commands, look at what they're telling you. If that's an R there, you're going from a register to a 16-bit hex number. Or this could be, as you were asking earlier, this could be X, Y, or Z. Because the X, Y, and Z registers are how large? 16-bit. They're 16 bits. You have to use the 16-bit addressing. All right? It's a given. Any questions so far? All right? All right. We go again. LDS. We're loading from, and again, the S stands for, the LD stands for load. S stands for what? SRAM. So I'm loading from SRAM. Now again, if I'm doing anything with SRAM, I immediately know how big, how many bytes is that instruction going to take. If I'm doing anything with SRAM, it's got to be 32-bit. It's got, because the top 16 bits are going to be the memory location, and the other bits are going to be for the opcode in my destination register. So anytime I'm dealing with SRAM, you're automatically talking a 32-bit instruction or 4 bytes. Okay? So again, LDS is to load from SRAM. Now, where are you going to load it to? Register. So I'm now grabbing something from SRAM. I need a 16-bit address, and I'm going to load that into the register. Yeah.
Can you use like the X register as K?
It's a 16-bit number.
So X.
Yeah. Oh, yeah. X. You could use the X register. X, Y, or Z here.
Okay.
Any one. Okay? Because, again, it's 16-bit. The in instruction is to grab something from an I.O. port and bring it in. Now, we go from 0 to 63 here because that's these are going to be the addresses for the I.O. port. D goes from 0 to 31 because it's the destination register. And all I do is I go in, I give it like a port PNC here or whatever, and then a read. All right? We'll get to these when we do the I.O. stuff. Same thing if I'm going to write something out to a port. A jump instruction is a 32-bit instruction because, again, what are we doing? We're jumping around in Flash now. Okay? How many address lines do I need for Flash? Huh? Come on. You're going to need at least 16 address lines. That's why, again, it's a 4-byte instruction. Because here I'm jumping from one place to another, not in SRAM, but in ROM, in Flash. All right? We'll get to this jump instruction in Chapter 3. All right? All right, now.
Should we know how, like, for like, should we know how big each memory location is in like the 2560?
Nah, you don't have to memorize it. I don't memorize it. I look it up. Yeah, yeah. And if you need it, you're going to just look it up. Okay? Yeah, I know. We're dealing with really three different AVR chips. Yeah, but I'm going to try to concentrate mostly on the 169P.
So using that STS, can you store a register into memory location,
STS. Yeah.
or is it only in SRAM that you can write to? Like, they're like SRAM and then there's like flash.
You're not going to be writing to flash. That's where your program goes. So you don't mess with flash. We will be reading stuff out of flash. I'll show you how to do that a little bit down the road, but yeah. Yeah, flash is just, that's where the program code goes, and you can put some initial data in there too. And then we can peel that data out and put it into SRAM if we want. Yeah. All right, part B. We're just going to load hex 11 into some memory locations starting at 100 through 105. So I just load it into any register. I just load the hex value into any register. Here it's R30. And then I just store R30. Notice it's the same register on the right-hand side. And then I just store it in these six memory locations. Okay? That's it. That stores it for me. That puts it into SRAM. So it's now stored. Then I load in the first memory location in the R20, the second location in the R16, and then I add them together. Load in the next memory location, load it in the R16, add them, and then just keep repeating that process. Okay? Some of you folks were just doing LDIs here. Okay? You can't do just LDIs. You got to store it. Okay? And then read it out. Okay? Each one of these, this was worth 5 points, and that one was worth 5 points. Okay? Is that okay? Any other questions on that? All right? Don't hesitate to ask. All right? Yeah, go ahead. Mr. Lebowski, go ahead. You see what you did. You had all LDIs. Yeah.
What was the one thing you were talking about where, like, I know it has something to do with why we can only load in the register 16 to 31, where when it's like 0005 actually becomes register 21 because it assumes the ones that
All right, give me an example. What are you talking about here? You want to do an LDI?
Yeah, like when we're loading it.
LDI. Okay, come on. I got to see it. All right, go ahead. What do you want to do?
Well, you said that when you see like 05,
Where?
you're adding the 16. That's when you were explaining why it only goes into register 16 to 31.
Yeah.
It was dropping a 1 from somewhere.
Right. In order to do right, there was. Let me bring up the slide for you. That's the beautiful thing about these. We can just jump around. I know exactly where you're talking about. Here we go. We're right here, right? This guy. So again, loading in this is an immediate, all right? It's not an LDD and it's not an LDS. It's a number. When I do LDI, I'm loading in an 8-bit number immediately into R16. Now, they want you to use 16 through 31, okay? But you notice, if I write down what 16 is a 1, it's a 5 bits, all right? 17, 18, 19, okay?
That's just because that's what they chose to use.
That's the architecture is set up that way. That is correct. And again, if we look at it, we're just going by these nibbles. Nibble 3, 2, 1, and 0. The first nibble is for the opcode. For LDI, it's always going to be an E. It's always going to be an E. All right? The second, and these two are going to be the 8-bit, the 8 bits, 4 bits are going to go here, 4 bits are going to go here out of this, like here, 0, 1. That's, all right? And then the thing you're asking about is, okay, this nibble, this is the 1. This guy is going to take, if I have all zeros sitting in here, that's going to be R16. If I have 0001 in here, that's going to go R17. That's how it works.
I'm good.
We're good. Okay. Yeah.
If you tried to load a 16-bit number with LDI, would it
Won't happen. You'll get an error.
It'll complain.
Yeah.
It'll just chop.
And the nice thing about this is, gang, the questions that you're asking, you can just go right to Atmel Studio 6 and start doing it, and you'll see it. The solutions manual's right in front of you, right here. All right? Really. That's where you get it, is the more you do, you can correlate the knowledge of Atmel is how much time, I can't tell you how much time I sit on the bus from Ambler, I'm running Atmel Studio 6. Yesterday, I'm watching my son chase the dog in the backyard. What am I doing? Running Atmel Studio 6. We have a new dog. We traded in our Trixie. Well, that's another story. Trixie got traded to the mother-in-law because she bought a new dog and it was just too much for her. She bought a real little cute. But our Trixie is gone. Now we have Cody. At least it's not named Biff or some preppy name like, Sky. The dog's from Long Island. Come on. It's where the men are men and well, I won't get to that. All right. All right, so let's fit. Any other questions? We're good. Because I'm going to have a quiz for you on Friday. Unless you want to do it now. Chapter 2. I can't quiz you on Chapter 3. Yeah. Oh, yeah. All right, yeah, Anton wants to look at the swapping. Can you give me, all right, these are new slides, so I got to figure out where it's at. All right, where did I do the swapping at, Anton? Looks like data transfer. That's down a little too far. Yeah, I was swapping something here, and I moved the slides around, so I apologize. I wanted to organize them a little better for you. Transfer to R16, R0, R3. Oh, here it is. All right. This is the one you're talking about, Anton, right? The swap. Yeah. Okay. Let's copy it. Let's put it in a beautiful thing. That's why we got Studio 6 sitting up here. All right. All right. So, again, what we're doing, I can expand. Can you guys read this in the back? Are you all right? Or do you want me to make it larger? Luke, you see this stuff? You want me to make it larger? Huh? Please. All right, then ask. I can't read your minds. Maybe I can. No. All right. So the first thing we're going to do is just load into, now again, load immediately an 8-bit number into R17. Then what do? We give it a 16-bit address to take the contents of R17 and write it into 2000. So we're sitting in SRAM over here at 2000. And what's going to go in there is 03. That 8-bit number goes into SRAM. Okay? All right, then we're going to load into R17 BA, and that's going to go to 2001. So BA goes there. All right, now, then we're going to use R0 and R1. Actually, if I... Here is R1, or R0, and here's R1 in SRAM. Right? That's where it is. So right now, all I've done is load it. Now, let's run this guy. Let's build it and run it. Now, let me put a... JMP, yeah. That's just to stop memory from shutting down when we want to look at it. All right. Oh, also, please note that even though registers R16 or R26 and 27 are for the X, 28, 29 are for the Y, 30 and 31 are for the Z, they also show you what the registers are right here. All right? If you take a look on the screen, there they are. Okay? It's easier to see. It's easier to see it. I forgot to show you that the other day, but okay. All right, so let's march our way down. Now let's go over to, I'm going to change it from flash to the RAM. And we're going to make this 2000. 2000. And there you see the 3 is now in its memory location right here. So we've got the 3 in there, and then you'll see the BA will go in there next. All right, now, yeah. Where are you at?
2000.
Well, I see the numbers here. Well, just follow what I'm doing here, and then we can play with your stuff in a minute. All right, where are we at here? All right, now we're going to load into, now you're going to see the Y register is now going to get loaded in with 2000 up here. So now you can see the Y register is loaded up with the address, okay, the 16-bit address. Now what we're going to do is, and if you notice, we've then loaded into R0 using the Y register, okay? When you're using the Y register, it's LD, it's not LDS, okay? All right? So now, and you'll notice, there it is right there. Then we're going to load in, what are the contents of the Y register? 2000. But now we want to add on, I'm going to do an LDD, which is loading. Anytime I'm doing an LD, where is the result going to go? Into a register. It's got to go into a register. The question is, do I do an LDS, an LD, or an LDD? LDD is loading with a displacement. What is the displacement we're having? The number 1. So now it's going to take the contents of Y, which is 2000, add 1 to it. So now we're going to be looking at 2001, which is that memory location right there, which is that guy right there, and it's going to load it into R1. All right, so now we can look at, you see R0 and R1 now have these contents in it. Now, what we want to do is we want to swap these two numbers. The reason I'm loading things into R0 and R1 is so I don't lose the data. So I have 03 and BA right there. Now what we're going to do is we want to flip these two numbers. So I've got the two numbers stored here. Now I just take the BA here and write it into here. So this now gets taken out. The BA is written there. And what do I need to do now? Grab the 3 from register R0 and just bring it into here. You see what I'm doing? Anytime you're doing swapping or massaging data and stuff like that, you're going to need to store it temporarily somewhere, and that's why you use R0, DRs. Yeah.
What is the LD? Like, what's the difference between that and the LDI?
Let's go look it up. Do you have your book? Appendix A. All right. Appendix A has every instruction. It's got the complete instruction set, and they have a little example in there, too. You're not going to survive without getting the book.
I have the book. Just not
All right, no, okay, all right. Well, if you take a look, I have to look up instructions too. I don't have them all up here all the time. I mean, that's what it's, all 3 neurons are fighting each other sometimes, all right? So it's just, I got to look stuff up, It's okay, it's all right. Don't expect you to have everything memorized.
Don't you use LD and ST when you're dealing with the X, Y, and Z registers?
Yes. That's what the abbreviated LD and ST is when you're working with the X, Y, and Z register. Yeah.
Why YL and YH instead of just Y?
Because right here?
Yeah.
Because YL is an 8-bit register. It's register R28. We go to, it's synonymous. YL is R20. I could have put in here, honestly, I could have, instead of using YL here, I could have put in, let's go look. It's 28 and 29. This right here is an 8-bit register, and that's YH. This is an 8-bit register, and it's YL. It's in your, yeah, it's in the, you look up how to use the Y register. It's there. It's there. Yeah. Answer your question? About the swap? Okay, so if you just run this last instruction, you'll see that the 0, 3, and the BA were just swapped. Okay? Now you mean, well, Doc, what are you doing this for? It's to exercising the instruction set. That's why I'm doing it. All right? So that's the method to the madness. Okay? All right, so we can go back to the PowerPoints? Okay? All right. All right, I want to, all right, so let's go to, let me see where I am here. Okay. All right, 30, oh, good, we got 15 minutes here. All right. While we're on this, let me jump down in the slides a little bit, just to where, since we are talking about the 16-bit addressing. Let me just finish off, and then I'll go back to the other stuff I wanted to show you. All right. LD, okay, we're doing, again, the LD is when you're dealing with the X, the Y, or the Z. All right, that's what you were asking, I think, earlier, okay? ST deals with the X, Y, or Z also, okay? By themselves, all right? So, again, I've got a, it's a 16-bit address, and it's going into RAM, all right? SRAM, okay? Now, you may, if you notice here, we have the end of RAM for the 169P is 4FF, and for the 2560, it's FFF. For the Mega 32, I think it's 3FF. All right. That's what the. But I'm going to show you whatever. There's a real simple way to get these numbers through software. Okay. But all right. So we have the X registers again. You asked. I think you asked over there. It's right here. XH is R27. It's synonymous. So in that code, I could have used LD R27 with an 8-bit number, and it would have put it right there, an R27. Same thing as doing XL and XH. R26 has the lower part for Y. R28 has the lower byte for YL. 29 has the upper byte, the higher order byte for YH, and the same thing with the Z register. Okay? Again, these three registers are nice ways for me to go banging in and out of RAM, SRAM. That's what they're there for. All right? The Z register is actually used for a couple other things, and we'll get to that when we get to looping and branching and stuff like that. These are what we call indirect addressing, because, again, we're not doing... My pens. You can do an LDI R16 16-bit address, and we did that in the example that we had today. What these are, or the nice thing about it is this is a load immediate, because it's immediately taking in that 16-bit. Go and grab it in SRAM and put it in there. The nice thing about it is we can increment and decrement these registers so we can automatically start scanning things in and out. And I'll show you what I mean by that. Can't do what? No, this loads the contents.
Oh,
Yeah, right. Oh, I'm sorry. No, you know what? Yeah. LDS. I'm sorry. You're right. You got LDS. Because I'm going from SRAM. LDI would have to be an 8-bit number.
Looks like the same as K, like in the other slides, like X that we had in the last slide, and we put on.
Well, when LDS, like, if we go back, well, let me finish here, then we'll get, yeah, that's all right. There's a lot of good discussion today. That's good. All right. So here that goes in R17. All right. Now, if you notice, again, Mr. Daniels, right? Yeah. If you notice here, I'm loading in A3 into R26. That's the same thing. I could have used XL here instead of R26. I load that into R27. That's XH. Okay. Wait, what?
If you were going to do XL or XH, would you have to do LD instead of LDI? Or can you do LDI?
No.
so you use R26.
Yes. I'm using LDI because I'm loading in here the actual number.
But what if you were going to use XL instead, or XL and XH?
That's an 8-bit. That's an 8-bit address. I have to put in 8 bits.
You can still do LDI. You can use, like, for instance, you could say LDI XL0. That doesn't work though. I tried that yesterday, but it won't work.
LDI.
XL, 0x83.
Yeah. Yeah.
That's what he was at.
Oh, okay. Yeah. Yeah.
Doesn't-
Yeah.
When you put XL or YL, don't you have to use LD?
Let's run it. Let's grab this code and run it. I mean, that's the beauty of having it here. Jay, tell them what to do with the slides. Abu, tell them what to do with the slides. Read them. And? Come on, Abu. How do you practice? You hit Control C, which is a copy. We go over to Atmel Studio 6. We get everything out of here. We stop debugging. We get all that out of there. You hit Control V. And I got 2 jumps in here. I only need 2 jumps. And then we hit Build. We build the solution. And we start running it. Okay? Now, that did that. Now, Michael, you had a question about this. What do you want to do?
No, when you, instead of putting R26, when you put XL,
Okay, all right, let's stop debugging. Hit this. And you want XL here? XL. All right. Let's see what it says. Oh, we're good. Oh, I wanted to show you something. If you do get errors, it will tell you the line numbers that it's in, but you don't have the line numbers here. If you go on to Blackboard under Atmel AVR links and all this stuff, tutorials, all the way at the bottom, I put it on there yesterday how to get the line numbers. All right. So if you go up here to Tools, go to Options. All right. Then I think I need to go to Text Editor. Yeah, that's it. Text Editor, all languages, and then hit Display Line Numbers. Okay? Click on that. Yeah, that's right, because it's looking for XL and XH. Yeah. All right, again, let me, all right, please, let me bring up, okay, hold on. All right. Again, the importance of the instruction set and understanding what it's doing. If you notice here, here's my LDS and here's my LDs. Notice what the LDs all have affiliated with them. All these LDs, what do they have? Not that, but the X, Y, all you see on this whole slide here is the X, Y, and Z registers. And that's all you see is LD. You'll see an LDD because that's loading with a displacement. All right? So that's the importance of understanding. This is table 2.1 right out of the textbook. Okay? I can't tell you how important it is to understand what these are all doing. Okay? It's the difference between getting it and not getting it. Okay. Yeah, the Phillies lost last night. And Papelbon's out for seven games. No, go ahead. Yeah, I saw that too. Not a good picture on the front of the Inquirer. Yeah, I wouldn't want to be a fan there either.
Can you write directly from one memory location to another, or do you have to always store it and then
Well, is there a command that? Yeah, there's my stores. All right. Store register to memory location. They're all. You don't see any little, K's. You see any K's running around here? No K's. It's not okay. No K's. That's why you have the registers. That's why you use them. Again, it's so on the Intel 80, in the Intel series, you had 4 registers to play with: A, B, C, D. The accumulator, the base, the counter, and accumulator, base, counter. D was for data. You could play with any of those 4 registers. If you're working with a PIC processor, they give you 1 register, 1 W register. That's it. That's all you got. So everything's going in and out of that register to memory. Here we have 32 registers that we can bop. That's how they set up the architecture. That's the Harvard architecture that they have. The whole idea is to, very good point. The nice thing about this is most of the instructions, and that's what makes it fast, it's 1 clock cycle to execute it. You can have on the 8086, if you got some weird command, it could be like 20 or 30 clock cycles. So you're gagging the processor. So a lot of these, if you go back and look, Appendix A, can I borrow your book? Appendix A. Sorry there. In Appendix A, it summarizes not only the commands, and we're going to get into this in Chapter 3, because we're going to be doing timing. We're going to be doing timing, and if you look at it in Appendix A, all right, let's take STS. If you look at the STS command, the nice thing about it is it tells you what flags it affects. The STS doesn't affect any flags because you're just storing stuff. You're not doing any logical or arithmetic operations. But if you notice to the right of that, it says the number of cycles. It takes 2 clock cycles to execute an STS. Okay? It's different clock cycles for each different one. All right? If I do, let's go to, we out of time? 2 minutes? Okay. Let me do an add. Let's go all the way up to add. We go to the beginning. Yeah, and also it has the instruction summary here, and it tells you what flags are affected also. But let's go to the add. Adds 2 registers, and an add affects the following flags: the H, S, V, N, Z, C. It affects all those flags, can be affected. You look to the right, and it says it's done in 1 clock cycle. Pretty darn good. Yeah. So the faster your processor, it's chewing them up. All right? Okay, thank you. Amigon. So, Michael, does that answer? Okay, good. This is healthy, man. There's a lot of stuff that's going to be coming at you. So, all right, let me get out of here. And 10:49. All right. Please take a look at this. I'm gonna just do a couple of things on Friday. I'm gonna show you how to get RAM end and RAM beginning, and then we're gonna go right to chapter 3. Okay. All right. And look over your homework. All right. Hey, have a good one.